As we begin our journey through the mysterious galaxies revealed by the James Webb Space Telescope, let's first understand what makes this remarkable instrument so revolutionary. The James Webb Space Telescope represents a quantum leap in our ability to observe the cosmos, particularly the distant and ancient universe that was previously hidden from our view. For decades, astronomers relied primarily on the Hubble Space Telescope, which was launched in 1990 and has provided countless breathtaking images of cosmic objects. However, Hubble has limitations. It observes primarily in visible and ultraviolet light, wavelengths that are easily blocked by cosmic dust and that don't capture the most distant objects in our universe effectively. Webb, on the other hand, observes primarily in infrared light. As you continue to relax and perhaps feel your eyelids growing heavier, consider what this means. Infrared light is essentially heat radiation, with wavelengths longer than those of visible light. This capability gives Webb two significant advantages over previous telescopes. First, infrared light can penetrate cosmic dust clouds that block visible light. These dust clouds are common throughout the universe, obscuring many interesting cosmic phenomena from view. By observing in infrared, Webb can see through these clouds, revealing previously hidden stars, planets, and galaxies. Second, and perhaps more profoundly, infrared observation allows Webb to see the most distant objects in our universe. Due to the expansion of the universe, light from very distant galaxies is stretched, or redshifted, from visible wavelengths into infrared wavelengths. The more distant the galaxy, the more its light is stretched. Some of the most distant galaxies are so redshifted that their light has moved entirely out of the visible spectrum and into the infrared. Webb's infrared capabilities allow it to detect these extremely redshifted galaxies, effectively looking back in time to the early universe. Webb's primary mirror, with its distinctive honeycomb pattern of 18 hexagonal segments, spans 21 feet in diameter, making it the largest space telescope ever launched. This large mirror allows Webb to collect more light than Hubble, enabling it to see fainter and more distant objects. The mirror is made of beryllium, a lightweight metal, and coated with a thin layer of gold, which efficiently reflects infrared light. The design of Webb's mirror was dictated by the constraints of space launch. No existing rocket could accommodate a solid 21-foot mirror, so engineers designed a folding mirror that could fit within the rocket fairing and then unfold once in space. This innovative design allowed for a much larger mirror than would otherwise have been possible. Behind this magnificent mirror, a tennis court-sized sunshield, made of 5 layers of a material called Captain, protects the telescope's sensitive instruments from the heat of the sun, Earth, and Moon. This sunshield is crucial because Webb's instruments must be kept extremely cold, around -388 degrees Fahrenheit or 40 Kelvin, to detect the faint infrared signals from distant galaxies without interference from the telescope's own heat. The deployment of this sunshield was one of the most complex and risky aspects of Webb's mission. The shield had to unfold in space, a process involving hundreds of moving parts, any of which could have failed and compromised the mission. The successful deployment of the sunshield, along with the unfolding of the primary mirror, represented a triumph of engineering and a crucial milestone in Webb's journey to becoming operational. Webb carries 4 main scientific instruments, each designed to analyze different aspects of the infrared light it collects. The near-infrared camera, or NIRCam, is Webb's primary imager, designed to detect light from the earliest stars and galaxies. It can observe in the near-infrared wavelength range from 0.6 to 5 microns, allowing it to see objects approximately 13.6 billion light-years away. The near-infrared spectrograph, or NIRSpec, can observe 100 objects simultaneously, analyzing the spectrum of light from each to determine their physical properties such as temperature, mass, and chemical composition. This multiplexing capability makes NIRSpec highly efficient for studying large samples of galaxies. The mid-infrared instrument, or MIRI, sees the longest wavelengths of Webb's instruments, from 5 to 28 microns. This allows it to observe distant redshifted objects, as well as newly forming stars and planets that are still enshrouded in dust. MIRI includes both a camera and a spectrograph, providing both images and detailed spectral information. Finally, the Fine Guidance Sensor Near Infrared Imager and Slitless Spectrograph, or FGS-NIRISS, helps Webb point precisely and can detect the atmospheres of exoplanets as they transit in front of their host stars. This instrument plays a crucial role in Webb's search for potentially habitable worlds beyond our solar system. Webb orbits the Sun at what astronomers call the second Lagrange point, or L2, about 1 million miles from Earth. This location allows the telescope to maintain a stable position relative to Earth and the Sun, with its sunshield effectively blocking heat from both bodies, as well as from the Moon. The L2 point is one of 5 Lagrange points in the Earth-Sun system, where the gravitational forces of the two bodies balance in such a way that a spacecraft can maintain a relatively stable position. This distant orbit presents both advantages and challenges. On the positive side, it provides a stable thermal environment, far from the heat of Earth, which is essential for Webb's sensitive infrared observations. However, it also means that Webb is too far from Earth for astronauts to visit and repair, unlike Hubble, which was serviced multiple times by Space Shuttle missions. This makes Webb's initial deployment and operation all the more critical, as there are no opportunities for physical repairs or upgrades. The development of Webb was a long and sometimes challenging process. The project was first proposed in the late 1990s as the Next Generation Space Telescope, with an initial cost estimate of $500 million and a planned launch in 2007. However, as the design evolved and technical challenges emerged, the cost increased and the launch date was repeatedly delayed. The final cost of Webb was approximately $10 billion, and it was eventually launched on December 25, 2021, aboard an Ariane 5 rocket from French Guiana. Despite these challenges, the scientific potential of Webb was deemed worth the investment. The telescope is designed to address 4 main science themes: the end of the cosmic dark ages, the assembly of galaxies, the birth of stars and protoplanetary systems, and the origins of life. These themes encompass some of the most fundamental questions in astronomy and astrophysics, from the formation of the first galaxies after the Big Bang to the potential for life on planets around other stars. Since it began its scientific operations in July 2022, Webb has been sending back images and data that have astounded astronomers and the public alike. Its first deep-field image, released on July 11, 2022, showed thousands of galaxies in a patch of sky the size of a grain of sand held at arm's length. This image, centered on the galaxy cluster SMACS 723, included galaxies seen as they appeared more than 13 billion years ago, less than a billion years after the Big Bang. Webb has also provided unprecedented views of objects within our own solar system, from detailed images of Jupiter's storms and auroras to observations of Neptune's rings and moons. It has detected water vapor in the atmospheres of exoplanets, offering new insights into worlds beyond our solar system. And it has revealed the detailed structure of nearby galaxies, showing star formation regions and dust lanes with unprecedented clarity. But perhaps most exciting are the surprises, the observations that challenge our existing theories and force us to reconsider our understanding of the cosmos. As you continue to relax and perhaps drift closer to sleep, we'll explore some of these surprising discoveries in the realm of distant and mysterious galaxies. Webb's revolutionary capabilities have allowed astronomers to observe galaxies that existed when the universe was less than 2% of its current age. These observations are challenging our understanding of how quickly galaxies formed after the Big Bang and how they evolved over time. Before Webb, astronomers generally believed that the earliest galaxies would be small, irregular, and relatively simple in structure. This belief was based on the idea that galaxies would need time to grow and develop complex structures through mergers and internal processes. However, Webb has revealed that some very early galaxies are surprisingly large, massive, and structured, suggesting that galaxy formation and evolution may have proceeded more rapidly than previously thought. One particularly surprising discovery is the presence of mature, disk-shaped galaxies in the early universe. These galaxies, with their organized spiral structures, were thought to take billions of years to develop as stars orbit the galactic center and gradually settle into a disk. Finding such structures when the universe was less than a billion years old challenges this timeline and suggests that some galaxies may have formed their disks much more quickly than previously believed. Webb has also revealed unexpected diversity in early galaxies. Rather than finding a uniform population of small, irregular objects, astronomers are observing a wide range of sizes, shapes, and compositions. Some early galaxies appear to be actively forming stars at tremendous rates, while others seem to have already exhausted their star-forming gas. Some show signs of interaction and merger with other galaxies, while others appear isolated. This diversity suggests that multiple formation pathways may have been at work in the early universe. Another surprising finding is the presence of supermassive black holes in very early galaxies. These black holes, with masses millions or billions of times that of our Sun, were thought to grow gradually over billions of years, as they consume surrounding matter and merge with other black holes. Finding them fully formed in the early universe raises questions about how they could have grown so large so quickly. One possibility is that these black holes formed directly from the collapse of massive gas clouds in the early universe, bypassing the usual process of stellar evolution and collapse. Another is that black hole mergers were more common in the dense environment of the early universe, allowing rapid growth through multiple merger events. Webb's ongoing observations of these early supermassive black holes may help distinguish between these possibilities. The chemical composition of early galaxies has also provided surprises. Elements heavier than hydrogen and helium, which astronomers collectively call metals, are primarily created inside stars and then dispersed when those stars die, particularly in violent supernova explosions. This process takes time. Multiple generations of stars must live and die to enrich a galaxy with significant amounts of these heavier elements. Yet Webb has detected significant amounts of metals in some very early galaxies, suggesting that multiple generations of stars had already lived and died in these galaxies, despite the universe being less than a billion years old at the time. This finding challenges our understanding of how quickly stars can form, evolve, and die in the early universe. As we transition to our first cosmic lullaby, consider the vastness of time and space that Webb allows us to explore. The light from the most distant galaxies observed by Webb has been traveling for over 13 billion years before reaching the telescope's mirrors. When that light began its journey, the Earth had not yet formed, and the universe was still in its infancy. In our next segment, we'll explore one of the most distant galaxies ever observed, GNZ 11, and the surprising discoveries Webb has made about this ancient cosmic object. But for now, let your mind drift among the stars, imagining the silent, patient journey of light across the vast expanse of space and time. Cosmic Lullaby 1. The dance of light across the cosmos. As your body continues to relax and your mind begins to drift, imagine the gentle dance of light across the cosmos. Photons, the fundamental particles of light, traveling silently through the vast emptiness of space. Each photon, born in the heart of a distant star or galaxy, embarks on a journey that may last billions of years. These ancient messengers carry with them the secrets of their origins, the temperature, composition, and motion of the objects that emitted them. They travel in perfect straight lines unless deflected by gravity or absorbed and re-emitted by matter they encounter. Across the immense cosmic distances, these photons spread out, becoming ever more dilute, yet never losing their intrinsic nature. A single photon that left a galaxy 13 billion years ago still carries the exact same energy it had when it began its journey. though that energy has been stretched by the expansion of the universe, shifting from visible light to the infrared. Imagine these countless photons streaming in all directions from billions of galaxies, creating an intricate, invisible tapestry of light that permeates the universe. Some of these photons, by the sheer chance of cosmic geometry, are destined to fall upon the golden mirrors of the James Webb Space Telescope. There, after their epic journey across space and time, they are collected, focused, and detected, their ancient message finally received and decoded by human minds eager to understand the cosmos. What stories they tell, these travelers from the distant past, stories of galaxy birth and evolution, of star formation and destruction, of the grand cosmic drama that has been unfolding since the beginning of time. As you continue to relax and perhaps drift closer to sleep, allow your mind to follow these photons on their silent journey through the cosmos, from the heart of a distant galaxy to the mirrors of Webb, carrying with them the secrets of the universe, waiting patiently to be discovered. The dance of light across the cosmos is an eternal ballet, choreographed by the fundamental laws of physics. Photons born in the fusion fires of stars, in the swirling maelstroms around black holes, in the cooling afterglow of the Big Bang itself, all follow the same rules, moving at the unchanging speed of light through the expanding fabric of spacetime. Some photons travel unimpeded for billions of years, crossing vast cosmic voids where matter is scarce. Others encounter obstacles, clouds of dust and gas, the atmospheres of planets, the surfaces of moons and asteroids. Some are absorbed and re-emitted, changing their energy and direction. Others are scattered or reflected, their paths altered but their essential nature unchanged. The photons that reach Webb's mirrors have survived this cosmic obstacle course, carrying with them information about everything they've encountered along the way. The patterns of absorption lines in their spectra tell of the elements they've passed through. The degree of their redshift reveals the expansion of space during their journey. Their polarization may indicate the presence of magnetic fields or the scattering effects of dust. In this way, each photon becomes a cosmic historian, recording the conditions it has witnessed throughout its long journey. And when these photons finally reach Webb, they complete their purpose: to connect distant corners of the universe with our human consciousness, to allow us to see and understand places we could never physically visit. Now, as we return to our exploration of the mysterious galaxies revealed by Webb, remember that there's no need to hold onto every detail. Simply allow the gentle flow of cosmic information to wash over you as you transition towards sleep. GNZ11, Galaxy at the Edge of the Universe. As we continue our journey through the mysterious galaxies revealed by the James Webb Space Telescope, let's turn our attention to one of the most distant galaxies ever observed, GNZ11. This ancient cosmic object exists at what astronomers call the edge of the observable universe, a place so distant that we see it as it was just a few 100 million years after the Big Bang. GNZ11 was first identified by the Hubble Space Telescope, which detected this faint, red smudge of light in the constellation Ursa Major. Based on Hubble's observations, astronomers estimated that GNZ11 has a redshift of approximately 11.1, meaning we see it as it appeared about 13.4 billion years ago, just 400 million years after the Big Bang. This made GNZ11 the most distant galaxy ever observed by Hubble. To understand the significance of this redshift value, it helps to understand how astronomers measure cosmic distances. When light travels through the expanding universe, its wavelength gets stretched, shifting toward the red end of the spectrum. The more distant an object, the greater this redshift. A redshift of 11.1 means that the wavelength of light from GNZ11 has been stretched to 12.1 times its original value, an extraordinary amount that places this galaxy near the very limit of what was observable before Webb. However, Hubble's capabilities were limited when it came to studying this ancient galaxy in detail. The galaxy appeared as little more than a tiny red dot in Hubble's images, revealing little about its structure or composition. This is where the James Webb Space Telescope's revolutionary capabilities come into play. With its superior infrared sensitivity and larger mirror, Webb has provided astronomers with unprecedented views of GNZ11, revealing details that were previously invisible. As you continue to relax and perhaps feel your body becoming heavier against your bed or chair, let's explore what Webb has discovered about this ancient cosmic object. One of the most surprising findings is that GNZ11 appears to have a more complex structure than astronomers expected for a galaxy so early in the universe's history. Rather than being a shapeless blob of stars, as many early universe galaxies were thought to be, GNZ11 shows signs of organization, with what appears to be a disk-like structure and possibly even the beginnings of spiral arms. This level of organization is unexpected because galaxies are thought to develop their structure gradually over billions of years, through processes like mergers with other galaxies and internal dynamics, driven by gravity and star formation. Finding a galaxy with a developed structure so early in the universe's history challenges our understanding of how quickly galaxies can evolve. The traditional model of galaxy formation suggests that the first galaxies should be small and irregular, forming as matter collapses under gravity in the early universe. These small galaxies would then merge over time to form larger structures, gradually developing the organized patterns we see in mature galaxies like our Milky Way. This process was thought to take billions of years, with fully formed spiral galaxies not appearing until the universe was several billion years old. GN-Z11 challenges this timeline. Its apparent disk structure suggests that organized galaxies may have formed much earlier than previously thought, perhaps through more rapid collapse of gas clouds, or through different formation mechanisms entirely. This finding has prompted astronomers to revisit their models of early galaxy formation and consider alternative pathways that could lead to more rapid development of galactic structure. Even more surprising are Webb's findings about what's inside GNZ11. Using its spectroscopic instruments, Webb has analyzed the light from this galaxy in detail, breaking it down into its component wavelengths to determine the galaxy's composition and properties. These observations have revealed something truly unexpected. GNZ11 contains elements that shouldn't exist in such abundance so early in the universe's history. Elements heavier than hydrogen and helium, which astronomers collectively call metals, are primarily created inside stars and then dispersed when those stars die, particularly in violent supernova explosions. This process takes time. Multiple generations of stars must live and die to enrich a galaxy with significant amounts of these heavier elements. Yet Webb's observations suggest that GNZ11 contains a surprising amount of these metals, indicating that multiple generations of stars had already lived and died in this galaxy. Despite the universe being less than 400 million years old, when the light we're seeing left GNZ11. This finding challenges our understanding of how quickly stars can form, evolve, and die in the early universe. The presence of these metals suggests that star formation in the early universe may have proceeded much more rapidly than current models predict. Stars in the early universe may have formed, lived, and died on accelerated timescales, perhaps due to different conditions than those that exist today. Alternatively, the first generation of stars, known as population III stars, may have been much more massive than typical stars today, allowing them to evolve and die more quickly, enriching their surroundings with heavy elements on shorter timescales. Another possibility is that GNZ11 formed from gas that was already enriched with metals from even earlier generations of stars that existed before the galaxy itself coalesced. This would push the timeline for the first stars even further back toward the Big Bang, raising questions about how quickly matter could collapse to form stars in the very early universe. Another mystery surrounding GNZ11 is its brightness. This galaxy is surprisingly luminous for its age, shining with the light of a billion suns. This brightness suggests intense star formation, with new stars being born at a rate hundreds of times greater than in our Milky Way today. But what triggered this intense burst of star formation so early in the universe's history? And how could a galaxy accumulate enough gas to fuel such rapid star formation in such a short time after the Big Bang? One possibility is that GNZ11 formed in an unusually dense region of the early universe, where gas could collapse more rapidly to form stars. These cosmic overdensities are thought to be the seeds from which the largest structures in the universe, galaxy clusters and superclusters, eventually grew. If GNZ11 formed in such a region, it might have had access to more raw material for star formation than typical early galaxies. Another possibility is that GNZ11 experienced a major merger with another galaxy early in its history, triggering an intense burst of star formation as the gas from the two galaxies collided and compressed. Such mergers are known to trigger starbursts in nearby galaxies today, and they may have been even more common in the early universe when galaxies were closer together. Webb's observations have also revealed unusual structures within GNZ11 that astronomers are still working to understand. These include bright, compact regions that may be massive star clusters, or perhaps the earliest examples of what will eventually become globular clusters, dense collections of hundreds of thousands of stars that orbit many galaxies, including our own Milky Way. Globular clusters are among the oldest objects in the universe, containing stars that formed in the early epochs of galaxy evolution. Finding their precursors in a galaxy like GNZ11 could provide valuable insights into how these ancient stellar systems form and evolve. The clusters in GNZ11 appear to be even more compact and luminous than typical globular clusters in nearby galaxies, suggesting that they may be forming under different conditions or following different evolutionary paths. There's also evidence for what might be an active galactic nucleus, a region at the center of the galaxy where a supermassive black hole is consuming surrounding material, releasing enormous amounts of energy in the process. If confirmed, this would be one of the earliest supermassive black holes ever detected, raising questions about how such massive objects could form so quickly after the Big Bang. The formation of supermassive black holes is one of the great unsolved problems in astrophysics. These objects, with masses millions or billions of times that of our Sun, are found at the centers of most large galaxies today, including our Milky Way. But their origins remain mysterious. Did they form from the collapse of massive stars, growing gradually over billions of years through accretion and mergers? Or did they form directly from the collapse of massive gas clouds in the early universe, bypassing the stellar stage entirely? The possible detection of a supermassive black hole in GNZ11 favors the latter scenario, as there simply hasn't been enough time for a black hole to grow to supermassive proportions through conventional means in the short time since the Big Bang. This suggests that at least some supermassive black holes may have formed through direct collapse of gas clouds, a process that could occur much more rapidly than growth from stellar mass black hole seeds. As you continue to relax and perhaps drift closer to sleep, consider the immense journey that the light from GNZ11 has taken to reach us. The photons that Webb detected left this galaxy 13.4 billion years ago, traveling at the speed of light, 186,282 miles per second, across the expanding universe. During that time, the universe has grown significantly, so that GNZ11 is now located about 32 billion light-years from Earth in terms of current distance. This distinction between look-back time and current distance is important for understanding the true scale of the cosmos. The look-back time, 13.4 billion years in this case, tells us how long ago the light left the galaxy. But because the universe has been expanding during that entire journey, the galaxy is now much farther away than 13.4 billion light-years. The current distance of about 32 billion light-years represents how far we would have to travel to reach GNZ11 today, if we could somehow freeze the universe's expansion and move at the speed of light. These photons traveled uninterrupted through the vast emptiness of space, occasionally passing near other galaxies and massive objects whose gravity slightly altered their path. They traveled through the era of reionization, when the first stars and galaxies ionized the neutral hydrogen that filled the early universe, making it transparent to their journey. They continued as the universe expanded and evolved, as countless other galaxies formed and merged, as our own Milky Way took shape, as our Sun and Earth came into being, as life evolved on our planet, and as human civilization developed the technology to detect and interpret these ancient messengers from the edge of the observable universe. The journey of these photons is made even more remarkable by the fact that they represent some of the earliest light that we can ever hope to see. Before about 380,000 years after the Big Bang, the universe was opaque to light, filled with a hot, dense plasma that scattered photons before they could travel far. Only after the universe cooled enough for neutral atoms to form did it become transparent, allowing light to travel freely. This first light, called the cosmic microwave background, represents the earliest electromagnetic radiation we can detect. Galaxies like GNZ11 formed later, after gravity pulled matter together to form the first stars and galaxies. The light from GNZ11 thus represents a glimpse into a crucial period in cosmic history, the transition from the Dark Ages that followed the release of the cosmic microwave background to the cosmic dawn, when the first stars and galaxies began to shine. This period, roughly from 400,000 to 1 billion years after the Big Bang, saw the transformation of the universe from a relatively uniform distribution of hydrogen and helium gas to the complex, structured cosmos we see today, with galaxies, galaxy clusters, and the cosmic web of dark matter that underlies it all. GNZ11 stands at the threshold of this transformation, one of the earliest galaxies we can observe, a cosmic pioneer in the great drama of structure formation. Its light has traveled across nearly the entire observable universe to reach us, carrying information about conditions in the cosmos when it was less than 3% of its current age. What makes this journey even more extraordinary is that the light from GNZ11 is among the oldest light we can ever hope to see, limited by the fundamental nature of the early universe. Before about 380,000 years after the Big Bang, the universe was opaque to light, filled with a hot, dense plasma that scattered photons before they could travel far. Only after the universe cooled enough for neutral atoms to form did it become transparent, allowing light to travel freely. This first light, called the cosmic microwave background, represents the earliest electromagnetic radiation we can detect. Galaxies like GNZ11 formed later, after gravity pulled matter together to form the first stars and galaxies. As we prepare for our second cosmic lullaby, reflect on how Webb's observations of galaxies like GNZ11 are pushing back the frontier of our knowledge, allowing us to peer ever closer to the cosmic dawn, the era when the first stars and galaxies emerged from the primordial darkness to illuminate the universe for the first time. Cosmic Lullaby 2, the ancient light of distant worlds. As your mind continues to drift and your body sinks deeper into relaxation, imagine the ancient light of distant worlds washing over you like gentle waves on a cosmic shore. This light, born in stars that lived and died before our Earth even formed, has been traveling through the vast ocean of space for billions upon billions of years. Each photon, each particle of light, carries within it a story of its creation in the heart of a star or in the swirling maelstrom around a black hole, a story of its long journey across the expanding universe, a story of the ancient galaxy it once called home. These photons, traveling at the unchanging speed of light, have crossed distances so vast that our minds struggle to comprehend them. They have journeyed through the great cosmic voids between galaxy clusters, through regions of space untouched by matter, through the silent, empty darkness that makes up most of our universe. And now, after their epic journey, some of these ancient photons have found their way to the golden mirrors of the James Webb Space Telescope, where they are gathered and focused, their energy and information recorded and interpreted, their stories finally told. What tales they bring us of galaxies in their infancy, of the first generations of stars to shine in the cosmos, of a universe still young and rapidly evolving. These are the oldest stories in existence, written in the language of light, waiting patiently for billions of years to be read. As you continue to relax and perhaps drift closer to sleep, allow your mind to follow these ancient messengers on their silent journey through space and time. Feel the immense peace of the cosmic voids they have crossed, the patient persistence of their unvarying speed, the quiet dignity of their role as carriers of the universe's oldest information. Imagine a single photon, born in the heart of a massive star in GNZ 11 over 13 billion years ago. This photon, created in the nuclear fusion reactions that powered the star, escaped from the star's surface and began its long journey through space. It traveled outward, away from the dense cluster of stars that made up the young galaxy, passing through clouds of gas and dust that were themselves collapsing to form new stars. As it left the galaxy behind, this photon entered the vast intergalactic medium, the sparse gas that fills the space between galaxies. Here, the photon traveled largely unimpeded, its path a straight line through the expanding cosmos. Over billions of years, the universe around it grew, galaxies formed and evolved, stars lived and died. But the photon continued its journey, carrying with it information about its ancient source. After traveling for more than 13 billion years, covering a distance that expanded to over 30 billion light-years due to the universe's expansion, this photon approached our Milky Way galaxy. It passed by countless stars and planets, navigating the complex gravitational landscape of our galactic neighborhood. Finally, by chance or cosmic design, its path brought it to our solar system, to Earth, and to the waiting mirror of the James Webb Space Telescope. There, this ancient messenger was captured, its energy absorbed and converted into an electrical signal, its information preserved and analyzed. After a journey of 13.4 billion years, this photon completed its purpose: to connect us, observers in the present, with the distant past of our universe, to tell us the story of a galaxy that existed when the cosmos was in its infancy. Multiply this journey by trillions upon trillions of photons, each carrying its own piece of the cosmic story, and you begin to understand the profound connection that exists between us and the distant universe. Through these ancient messengers of light, we are linked to the farthest reaches of space and the earliest epochs of time, participants in a grand cosmic conversation that spans the history of the universe. Now, as we return to our exploration of the mysterious galaxies revealed by Webb, remember that there's no need to hold onto every detail. Simply allow the gentle flow of cosmic information to wash over you as you transition towards sleep, carried along by the ancient light of distant worlds, the bizarre, dead galaxy in the early universe. As we continue our journey through the mysterious galaxies revealed by the James Webb Space Telescope, we encounter a particularly puzzling discovery: a dead galaxy existing in the early universe. This finding challenges our fundamental understanding of galactic evolution and the timeline of cosmic development. In astronomical terms, a dead or quiescent galaxy is one that has stopped forming new stars. Most galaxies in the nearby universe cycle through periods of active star formation and relative quiescence. But finding a truly dead galaxy in the very early universe was unexpected and challenges existing theories. The galaxy in question was discovered by Webb as part of its systematic surveys of the early universe. As you continue to relax, allowing your body to become heavier and your mind to drift, let's explore this cosmic anomaly together. This particular galaxy exists at a redshift of approximately 7, meaning we see it as it appeared when the universe was less than 1 billion years old, roughly 5% of its current age. At this early epoch, most galaxies should be vigorously forming stars, fueled by the abundant gas that filled the early universe. Indeed, most galaxies observed at this distance appear blue in color, indicating the presence of hot, young stars that emit primarily blue and ultraviolet light. However, this particular galaxy appears red, not because of its extreme distance, though that is a factor, but because it lacks those hot, young blue stars. Instead, it is dominated by older, cooler stars that emit more red and infrared light. The absence of significant star formation is confirmed by Webb's spectroscopic analysis, which shows minimal emission lines typically associated with star-forming regions. To understand why this discovery is so surprising, it helps to consider the normal life cycle of galaxies as we understand it. Galaxies begin their lives with abundant supplies of cold gas, primarily hydrogen, which serves as the raw material for star formation. Over time, this gas collapses under gravity to form stars. As these stars age and die, they return some of their material to the interstellar medium, enriching it with heavier elements and potentially fueling new generations of star formation. Eventually, however, a galaxy may exhaust its supply of star-forming gas or lose it through various processes. Without new stars being born, the galaxy gradually becomes dominated by older, redder stars as the short-lived blue stars die out. In the nearby universe, this process typically takes many billions of years. With galaxies like our Milky Way still actively forming, stars more than 13 billion years after the Big Bang. Finding a galaxy that has already reached this dead state when the universe was less than 1 billion years old suggests that the entire process of galaxy formation, star formation, and eventual quiescence has been dramatically accelerated in this object. It's as if a person aged from infancy to old age in just a few years, a timeline that defies our understanding of normal development. This discovery is profoundly puzzling because it suggests that this galaxy formed its stars very early and very quickly, then somehow shut down star formation when the universe was still in its infancy. Conventional theories of galaxy evolution suggest that such early quiescence should be impossible. For a galaxy to stop forming stars, it must either exhaust its supply of star-forming gas or have that gas removed or rendered unsuitable for star formation. In the nearby universe, several processes can cause this. Galactic mergers triggering intense but brief starbursts that quickly consume available gas. Active galactic nuclei, powered by supermassive black holes generating winds that expel gas from the galaxy. Or environmental effects in galaxy clusters that strip gas from galaxies as they move through the intracluster medium. However, most of these processes are thought to take billions of years to unfold, or to require environmental conditions that shouldn't exist in the early universe. Finding a dead galaxy so early challenges these assumptions and forces astronomers to reconsider the timescales and mechanisms of galaxy evolution. Let's examine each of these potential quenching mechanisms in more detail, considering how they might operate in the early universe. First, the possibility of rapid gas consumption through intense star formation. If a galaxy forms in an unusually dense region of the early universe, it might accumulate gas very quickly and convert it to stars in a massive burst of star formation. This starburst phase could potentially exhaust the galaxy's gas supply in a relatively short time. However, even the most intense starbursts observed in the nearby universe typically convert only a small fraction of a galaxy's gas into stars before feedback mechanisms, such as supernovae and stellar winds, disrupt the star-forming regions and slow the process. For a galaxy to convert all of its gas to stars would require an extraordinarily efficient star formation process, beyond what we typically observe. Second, the role of active galactic nuclei and supermassive black holes at the centers of galaxies can, when actively accreting matter, generate enormous amounts of energy. This energy can heat surrounding gas, preventing it from cooling and collapsing to form stars, or drive powerful outflows that expel gas from the galaxy entirely. In the nearby universe, AGN are thought to play a crucial role in shutting down star formation in massive galaxies. However, the development of a supermassive black hole large enough to affect an entire galaxy was thought to take billions of years. Finding evidence of AGN quenching in the early universe suggests that supermassive black holes may have formed and grown much more rapidly than previously believed. Third, environmental effects. In the nearby universe, galaxies in dense clusters can have their gas stripped away as they move through the hot, diffuse gas that fills the space between cluster galaxies. This process, called ram pressure stripping, effectively removes the raw material for star formation, leading to quiescence. However, galaxy clusters take time to assemble and virialize, and the first massive clusters were not thought to be fully formed in the first billion years after the Big Bang. If environmental effects are responsible for quenching this early galaxy, it suggests that dense cosmic environments developed much more quickly than our models predict. Webb's detailed observations of this galaxy reveal additional puzzles. Despite being dead, the galaxy is surprisingly massive, containing the equivalent of tens of billions of solar masses in stars. This suggests that it underwent an incredibly intense period of star formation early in its history, forming the bulk of its stars in perhaps just a few tens of millions of years, an astronomical eye blink. To put this in perspective, our Milky Way forms stars at a rate of about 1 to 2 solar masses per year. At this rate, it would take tens of billions of years to build up the stellar mass observed in this dead early galaxy. This means that at its peak, this galaxy must have been forming stars hundreds or even thousands of times more rapidly than our galaxy does today. A truly extraordinary rate of star formation. The galaxy also shows signs of a well-developed structure, with a central bulge and what appears to be the remnants of spiral arms, further suggesting a complex evolutionary history that theories suggest shouldn't have had time to develop so early in the universe's history. The presence of a central bulge is particularly interesting, as these structures are thought to form through a combination of early star formation and the mergers of smaller galaxies. Finding a well-developed bulge in such an early galaxy suggests that the processes of galaxy assembly and structural evolution were already well underway less than a billion years after the Big Bang. The remnant spiral arms are even more puzzling. Spiral structure in galaxies is thought to be a relatively late development, requiring a stable disk of stars and gas that can support density waves or other mechanisms that create spiral patterns. Finding evidence of spiral structure in a galaxy from the early universe, and a dead one at that, challenges our understanding of how and when these features develop. Perhaps most intriguingly, Webb's observations suggest the presence of a supermassive black hole at the galaxy's center, with a mass potentially billions of times that of our Sun. While no longer active enough to generate the powerful jets and winds associated with active galactic nuclei, this black hole may hold the key to understanding the galaxy's premature death. The relationship between supermassive black holes and their host galaxies is complex and not fully understood. In the nearby universe, there's a tight correlation between the mass of a galaxy's central black hole and the mass of its bulge, suggesting that the two evolved together. Finding a massive black hole in this early dead galaxy provides an opportunity to study this relationship in its earliest stages. One theory suggests that this black hole grew rapidly in the early universe, perhaps through direct collapse of primordial gas clouds rather than the slower process of stellar evolution and mergers. As it grew, it may have generated powerful winds that expelled much of the galaxy's gas, shutting down star formation. This scenario, sometimes called quasar mode feedback, is thought to be an important quenching mechanism for massive galaxies. Another possibility is that the galaxy formed in an unusually dense region of the early universe, allowing it to evolve more rapidly than typical galaxies. These cosmic overdensities are the seeds from which galaxy clusters eventually grow, and galaxies that form within them may experience accelerated evolution due to the higher density of matter and the stronger gravitational forces at play. If this dead galaxy formed in such an overdensity, it might have accumulated gas more rapidly, formed stars more intensely, and exhausted its star-forming potential more quickly than galaxies in less dense regions. It might also have experienced more frequent interactions and mergers with other galaxies, potentially triggering both intense star formation and powerful AGN activity that could ultimately lead to quenching. As you continue to relax and perhaps drift closer to sleep, consider the implications of this discovery. If galaxies could form and die so quickly in the early universe, our understanding of cosmic evolution may need significant revision. The processes that drive galaxy formation and evolution may operate on much shorter timescales than previously thought. Or there may be additional mechanisms at work in the early universe that we have yet to understand. Webb's observations of this and similar dead early galaxies are ongoing, with astronomers around the world analyzing the data and developing new theories to explain these unexpected findings. Each new observation brings us closer to understanding the complex processes that shaped the early universe and ultimately led to the formation of galaxies like our own Milky Way. The existence of this galaxy also raises profound questions about the diversity of galactic evolution pathways. Rather than all galaxies following similar evolutionary tracks, there may be multiple routes through which galaxies form, evolve, and eventually see star formation. Some may burn bright and die young, like this early dead galaxy, while others may maintain steady star formation for billions of years, like our own Milky Way. This diversity of evolutionary pathways reflects the complexity of the processes involved in galaxy formation and evolution. Galaxies are not simple systems, but rather complex ecosystems where many processes, gravity, hydrodynamics, star formation, stellar evolution, supernova feedback, black hole growth and feedback, and interactions with other galaxies, all interact in complex ways. The balance of these processes determines a galaxy's evolutionary trajectory, and small differences in initial conditions or environment can lead to vastly different outcomes. The dead early galaxy observed by Webb represents one extreme in this spectrum of possibilities. A galaxy that formed, evolved, and died within the first billion years of cosmic history. By studying this extreme case, astronomers hope to better understand the full range of galaxy evolution pathways and the factors that determine which path a particular galaxy will follow. As we prepare for our third cosmic lullaby, reflect on how the universe continually surprises us, challenging our assumptions and expanding our understanding. Even as our knowledge grows, the cosmos reveals new mysteries, inviting us to look deeper and think more broadly about the processes that shape our universe. Cosmic Lullaby 3. The silence between the stars. As your body continues to relax and your mind drifts further toward the edges of consciousness, imagine the profound silence that exists between the stars. In the vast emptiness of intergalactic space, where atoms may be separated by distances greater than those between stars in our galaxy, there exists a quietude more complete than anything we can experience on Earth. This cosmic silence is not merely the absence of sound, for sound cannot travel through the vacuum of space, but a fundamental stillness, a pause in the cosmic symphony of creation and destruction. It is in these silent voids that we can contemplate the rhythm of the universe, the slow pulse of galactic evolution that plays out over billions of years. Like the dead galaxy we've been discussing, these silent regions remind us that the universe has its own pace, its own cycles of activity and rest. Stars are born in brilliant nurseries of gas and dust, shine for millions or billions of years, and then fade, returning their enriched material to the cosmic medium from which new stars will eventually form. Galaxies, too, have their seasons, periods of intense star formation followed by quieter epochs where few new stars are born. Some, like our mysterious dead galaxy, experience a brief but brilliant youth before falling silent, while others maintain a steady, measured pace of star birth over cosmic time. As you continue to relax and perhaps drift closer to sleep, allow yourself to feel the immense peace of these cosmic silences. Feel the patient timescales of the universe, where a million years is but a moment, and the slow, steady processes that have shaped the cosmos since its beginning. In this cosmic silence, there is no hurry, no urgency. The stars and galaxies follow their paths according to the fundamental laws of physics, unfolding their stories across the vast canvas of space and time. And we, briefly awakened stardust, have the privilege of witnessing and understanding a small part of this grand cosmic narrative. The silence between the stars is not empty, but filled with potential tenuous gases that may someday collapse to form new stars, invisible dark matter that shapes the large-scale structure of the universe, and the omnipresent dark energy that drives the accelerating expansion of space itself. In this silence, the future of the cosmos is written, waiting patiently to unfold over billions of years. Imagine drifting through this cosmic silence, far from any star or galaxy, in the vast voids between cosmic structures. Here, in the darkness and quiet, you might float for millions of years without encountering a single atom. The temperature approaches absolute zero. The closest physical systems can come to perfect stillness. The only light comes from distant galaxies, tiny pinpricks of luminosity in an otherwise perfect blackness. Yet even in this profound silence and emptiness, the universe is not truly still. Space itself expands, carrying galaxies ever farther apart. Quantum fluctuations ripple through the vacuum, creating and annihilating virtual particles in an endless dance of possibility. Neutrinos and cosmic rays pass by, nearly massless messengers from distant cosmic events. And the faint whisper of the cosmic microwave background, the afterglow of the Big Bang itself, permeates everything, a constant reminder of the universe's fiery birth. In this cosmic silence, time seems to lose meaning. Without the rhythms of day and night, without the cycles of seasons or years, there is only the eternal now, stretching backward to the beginning of time and forward to the distant future. Here, in this timeless void, you might contemplate the full sweep of cosmic history, from the first moments after the Big Bang, through the formation of the first stars and galaxies, to the present day, and onward to the far future when the last stars will flicker and die, leaving only black holes and the ever-thinning gas of an expanding universe. Now, as we return to our exploration of the mysterious galaxies revealed by Webb, remember that there's no need to hold onto every detail. Simply allow the gentle flow of cosmic information to wash over you as you transition toward sleep, carried along by the profound silence between the stars. Ring galaxies and cosmic structures. As we continue our journey through the mysterious galaxies revealed by the James Webb Space Telescope, let's turn our attention to some of the most visually striking objects in the cosmos. Ring galaxies. These rare and beautiful formations challenge our understanding of galactic evolution and structure, and Webb's observations have revealed thousands of new examples, each with its own unique story to tell. Ring galaxies are among the most unusual structures in the universe. Unlike the more common spiral and elliptical galaxies, ring galaxies feature a distinct circular or ring-shaped structure, often surrounding a central core. The rings themselves are typically regions of intense star formation, glowing brightly with the light of young, hot stars, while the centers may contain older stellar populations, or in some cases, appear almost empty. As you continue to relax, allowing your breathing to become slower and deeper, let's explore how these cosmic rings form and what Webb has discovered about them. The most widely accepted theory for the formation of ring galaxies involves galactic collisions. When a smaller galaxy passes through the center of a larger disk galaxy along a path perpendicular to the disk, it creates a gravitational disturbance that propagates outward through the larger galaxy like a ripple in a pond. This ripple compresses gas and dust as it moves, triggering star formation in a ring-shaped pattern around the center of the galaxy. This collision scenario is elegantly simple in concept, but involves complex gravitational dynamics. The intruder galaxy essentially acts like a stone dropped into a pond, with the disk galaxy's stars and gas responding to the gravitational disturbance by moving outward in a wave. The mathematics describing this process are similar to those describing ripples on a water surface, though complicated by the three-dimensional nature of the galaxy and the fact that stars, unlike water molecules, don't collide with each other, but respond individually to the changing gravitational field. The Cartwheel Galaxy, located about 500 million light-years away in the constellation Sculptor, is perhaps the most famous example of a ring galaxy formed through this collision process. Its distinctive wheel-like appearance, with a bright outer ring, spoke-like structures, and a central hub, makes it an ideal case study for understanding these cosmic collisions. Webb's infrared observations of the cartwheel have revealed unprecedented details of its structure, showing the distribution of dust and gas, as well as both young and old stellar populations. The collision that created the cartwheel is estimated to have occurred about 200 to 300 million years ago, a relatively recent event in cosmic terms. The intruder galaxy, having passed through the disk, is now visible as a small, distorted galaxy some distance away from the cartwheel. Over time, the cartwheel will likely evolve back into a more conventional spiral galaxy as the ring expands and dissipates, though this process will take hundreds of millions of years. This collision scenario explains many of the ring galaxies we observe, such as the famous Cartwheel Galaxy. However, Webb's observations have revealed that the story may be more complex and varied than previously thought. One of Webb's most surprising discoveries is a galaxy with 9 nearly perfect concentric rings, a structure that cannot be easily explained by a single collision event. This multi-ringed galaxy, observed as part of Webb's survey of distant galaxy clusters, suggests that multiple processes may be at work in shaping these unusual structures. This extraordinary galaxy, temporarily designated JWST Org-1, James Webb Space Telescope, Outstanding Ring Galaxy 1, has captivated astronomers since its discovery. The 9 concentric rings are remarkably regular in their spacing and circularity, creating an appearance reminiscent of a cosmic bull's or the grooves on a vinyl record. The outermost ring spans approximately 100,000 light-years in diameter, roughly the size of our Milky Way galaxy, while the innermost ring is just a few thousand light-years across. One possibility is that this galaxy experienced multiple collision events, each creating its own ring that expanded outward over time. This scenario would require an unusual set of circumstances, perhaps multiple smaller galaxies passing through the disk galaxy along similar trajectories, spaced out over hundreds of millions of years. While not impossible, such a precise arrangement of multiple collision events seems improbable. Another theory suggests that internal processes within the galaxy, such as density waves similar to those that create spiral arms, might be capable of generating multiple ring structures under certain conditions. These density waves are oscillations in the gravitational field of the galaxy that can compress gas and trigger star formation as they move through the galactic disk. Under specific conditions involving the galaxy's mass distribution and rotation curve, these waves might form concentric ring patterns rather than the more common spiral structures. A third possibility involves resonances in the galaxy's gravitational field. Just as certain frequencies cause standing waves in a vibrating string or membrane-specific orbital frequencies in a galaxy's gravitational field can create resonant patterns in the distribution of stars and gas. These resonances might, under the right conditions, manifest as concentric rings of enhanced density and star formation. Whatever the explanation, JWST Org-1 represents a profound challenge to our understanding of galactic structures and evolution. Its perfect symmetry and multiple rings suggest processes at work that current models struggle to fully explain, highlighting how much we still have to learn about the diversity of galaxies in our universe. Webb's infrared capabilities have been particularly valuable for studying ring galaxies because they allow astronomers to peer through the dust that often obscures the central regions of these galaxies in visible light. This has revealed previously unseen structures and helped clarify the relationship between the rings and the galactic cores they surround. In many ring galaxies, the central region appears relatively empty in visible light images, leading to the impression that the collision has swept all material into the ring. However, Webb's infrared observations often reveal that these central regions contains significant populations of older, redder stars that are obscured by dust in visible wavelengths. This suggests that the collision primarily affects the gas and dust in the galaxy, which is compressed into the ring and triggers new star formation, while the existing stellar population remains relatively undisturbed. In some cases, Webb has observed ring galaxies where the central galaxy appears to be actively rebuilding itself after the collision that created the ring. Stars and gas that were not swept into the ring are gradually settling back toward the center, beginning the process of reconstructing a normal galactic structure. This provides a fascinating glimpse into the resilience and adaptability of galaxies in the face of dramatic disruptions. The process of rebuilding after a collision is a slow one, typically taking hundreds of millions to billions of years. Gas that was not swept into the ring gradually loses energy through various processes, causing it to sink toward the galaxy's center. As this gas accumulates, it can trigger new star formation in the central region. Meanwhile, stars that were temporarily displaced by the collision gradually return to more stable orbits, their paths determined by the galaxy's overall gravitational field. This rebuilding process is not simply a return to the galaxy's pre-collision state, but rather the creation of a new structure shaped by the collision event. The resulting galaxy often bears the marks of its violent history, with features such as a more prominent bulge, a different distribution of stellar populations, or unusual patterns of star formation that can persist for billions of years after the collision itself. Webb has also discovered ring galaxies at much greater distances than previously observed, allowing astronomers to study how these structures evolved throughout cosmic history. Surprisingly, ring galaxies appear to have been more common in the early universe than they are today, suggesting that galactic collisions were more frequent when galaxies were closer together in the younger, more compact universe. This finding aligns with our broader understanding of cosmic evolution. In the early universe, galaxies were packed more closely together in the smaller cosmic volume, making collisions and interactions more frequent. As the universe expanded, the average distance between galaxies increased, reducing the frequency of collisions. Additionally, many of the smaller galaxies that might have acted as intruders to create ring galaxies have already been absorbed into larger galaxies through mergers, further reducing the potential for new ring galaxies to form in the present-day universe. The study of thousands of newly discovered ring galaxies is helping astronomers understand not just how these particular structures form, but also broader questions about galaxy evolution and the role of mergers and interactions in shaping the galaxies we see today. One particularly intriguing aspect of ring galaxies is their star formation efficiency. The compression of gas in the expanding rings creates ideal conditions for the birth of new stars, resulting in star formation rates that can be tens or even hundreds of times higher than in typical spiral galaxies. This makes ring galaxies valuable laboratories for studying the process of star formation under extreme conditions. In a typical spiral galaxy like our Milky Way, star formation proceeds at a relatively modest pace, with new stars forming primarily in the spiral arms where gas is slightly compressed as it moves through the galaxy's density waves. In ring galaxies, however, the compression of gas is much more dramatic, creating dense clouds where gravity can overcome other forces more easily, leading to the collapse of these clouds and the formation of new stars. The star formation in these rings is not uniform, but often appears as a series of bright knots or clumps along the ring. These knots represent massive star clusters, containing hundreds or thousands of young, hot stars that formed nearly simultaneously from the same cloud of compressed gas. Webb's infrared observations can peer into these star-forming regions, revealing not just the bright, massive stars visible in optical wavelengths, but also the less massive stars, and even the protostellar objects still in the process of formation. Webb's observations have also revealed unexpected diversity in the composition of ring galaxies. Some show evidence of significant amounts of heavy elements, suggesting they formed from already enriched material, while others appear more pristine, composed primarily of hydrogen and helium with few heavier elements. This diversity hints at multiple formation pathways and histories for these unusual cosmic structures. The chemical composition of a galaxy provides important clues about its history and evolution. Elements heavier than hydrogen and helium, what astronomers call metals, are primarily created inside stars and then dispersed into the interstellar medium when those stars die. A galaxy with a high metal content has likely experienced multiple generations of star formation, with each generation enriching the galaxy's gas with more metals. Conversely, a galaxy with low metal content may be relatively young or may have experienced less star formation in its past. The diversity of metal content in ring galaxies suggests that these structures can form at different stages of a galaxy's life cycle. Some may be relatively young galaxies experiencing their first major collision, while others may be mature galaxies with a rich history of star formation before the collision event that created their ring structure. As you continue to relax and perhaps drift closer to sleep, consider the beautiful symmetry of these cosmic rings, perfect circles etched against the backdrop of space. Despite their apparent simplicity, each ring tells a complex story of galactic interaction and evolution, a story that Webb is helping us read with unprecedented clarity. The existence of ring galaxies also reminds us of the dynamic nature of the universe. Galaxies are not static, unchanging objects, but rather evolving systems that grow, interact, and transform over billions of years. The rings we observe are snapshots of a process in motion, expanding waves that will continue to evolve long after our brief observations. These cosmic rings also serve as natural laboratories for studying a wide range of astrophysical processes. The compression of gas in the rings triggers star formation under conditions different from those in typical spiral arms, allowing astronomers to test theories of star formation across a broader range of environments. The movement of stars and gas in response to the gravitational disturbance provides insights into the dynamics of galactic disks and the distribution of both visible and dark matter within galaxies. Moreover, the study of ring galaxies at different distances, and thus different cosmic epochs, allows astronomers to track how these processes have evolved over the history of the universe. By comparing nearby ring galaxies with those in the distant past, we can better understand how factors such as galaxy density, gas content, and metal enrichment have changed over time, and how these changes have affected the outcomes of galactic collisions. As we prepare for our fourth cosmic lullaby, reflect on how these ring structures represent both destruction and creation. The disruption of one galactic structure, leading to the beautiful, organized pattern of a ring and the birth of countless new stars within it. Cosmic Lullaby 4, Circles in the Void. As your mind continues to drift and your body sinks deeper into relaxation, imagine the perfect circles of ring galaxies suspended in the cosmic void. These luminous rings, spanning tens of thousands of light years, hang in the darkness like cosmic jewelry, adorning the velvet backdrop of space. There is something profoundly soothing about the circle, the most perfect of geometric forms. No beginning, no end, just a continuous curve that returns to itself, embodying both infinity and completion. Throughout human history, across cultures and civilizations, the circle has represented wholeness, unity, and the cyclical nature of existence. In the cosmos, too, we find circles and cycles everywhere we look. The orbits of planets around stars, the rotation of galaxies, the expansion and potential contraction of the universe itself, all follow curved paths through space and time. Even light, when passing near massive objects, follows the curved geometry of spacetime as described by Einstein's theory of general relativity. The ring galaxies we've been discussing are perhaps the grandest circles in the cosmos, formed through processes of disruption and renewal that mirror the cycles we observe throughout nature. A galaxy passes through another, creating a ripple that expands outward. Gas compresses and forms new stars, Those stars live out their lives and eventually return their material to the galaxy, perhaps to form new rings in future interactions. As you continue to relax and perhaps drift closer to sleep, allow your mind to follow the perfect curve of these cosmic rings, around and around without beginning or end. Feel the completeness they represent, the wholeness of a universe where destruction leads to creation, and every ending contains the seeds of a new beginning. Imagine floating in space, far enough from a ring galaxy to see its entire structure, a perfect circle of light against the darkness. From this distance, the individual stars are not visible, only their collective glow forming the luminous ring. The ring appears still, frozen in time, though in reality, each star within it is in constant motion, orbiting the galactic center at hundreds of kilometers per second. As you draw closer in your imagination, details begin to emerge. The ring resolves into countless individual stars, clusters, and nebulae. What appeared as a simple circle from a distance now reveals itself as a complex ecosystem of stellar birth, life, and death. Blue regions mark areas of intense star formation, where massive, short-lived stars burn brightly. Redder regions contain older stellar populations or areas rich in cosmic dust. Dark lanes cut through the ring where particularly dense dust clouds block the light from stars behind them. Closer still, you might focus on a single star-forming region within the ring. Here, the compression wave that formed the ring has concentrated gas and dust, creating the perfect conditions for new stars to form. Massive clouds of molecular hydrogen collapse under their own gravity, fragmenting into smaller clumps that will become individual stars or star clusters. Some of these protostars are already beginning to shine, their nuclear fusion reactions igniting as the pressure and temperature at their cores reach the necessary threshold. Around these young stars, disks of gas and dust orbit, gradually coalescing into planets, asteroids, and comets, new solar systems in the making. Perhaps some of these planets will eventually harbor life, born from the cosmic disruption that created the ring galaxy millions or billions of years earlier. In this cosmic cycle, there is no true death, only transformation. The stars that burn and die within these rings release the elements from which new stars, planets, and potentially life will form. We ourselves are part of this grand cycle, our bodies containing atoms forged in the hearts of long-dead stars that once may have shone within cosmic rings, much like those we've been discussing. The perfect circle of the ring galaxy thus becomes a symbol of the cosmic cycle of matter and energy, a cycle in which nothing is truly created or destroyed, but only transformed from one form to another. The hydrogen atoms in the water you drink may once have been part of a star that exploded billions of years ago, releasing its elements into space to be incorporated into new stars, planets, and eventually, living beings. As you continue to relax and drift towards sleep, feel yourself as part of this grand cosmic cycle, connected through the atoms of your body to the stars and galaxies we've been exploring. Like the perfect circle of a ring galaxy, your existence is both complete in itself and part of something larger, the great cosmic dance of matter and energy that has continued since the beginning of time and will continue long after our brief moment of awareness has passed. Now, as we return to our exploration of the mysterious galaxies revealed by Webb, remember that there's no need to hold onto every detail. Simply allow the gentle flow of cosmic information to wash over you as you transition towards sleep, carried along by the perfect circles etched in the void. Galactic jets and cosmic mysteries. As we continue our journey through the mysterious galaxies revealed by the James Webb Space Telescope, let's explore one of the most energetic and enigmatic phenomena in the cosmos: galactic jets. These immense streams of particles and energy extend from the centers of certain galaxies, stretching across millions or even tens of millions of light years, making them some of the largest coherent structures in the universe. As you continue to relax, allowing your body to become heavier and your mind to drift further, let's explore these cosmic fountains and the new mysteries Webb has uncovered about them. Galactic jets are typically associated with active galactic nuclei, or AGN, the extraordinarily bright central regions of certain galaxies, where supermassive black holes are actively consuming surrounding material. As matter falls toward a supermassive black hole, it forms a rotating disk of gas and dust called an accretion disk. The intense gravitational forces and friction within this disk heat the material to millions of degrees, causing it to emit enormous amounts of radiation across the electromagnetic spectrum. To understand the formation of these jets, we need to delve into the physics of black holes and their surrounding environments. A black hole itself, despite its name, is not truly a hole, but rather an extremely dense concentration of mass where gravity is so intense that nothing, not even light, can escape once it passes the event horizon, the boundary beyond which escape becomes impossible. However, before matter crosses this point of no return, it typically forms an accretion disk around the black hole. This accretion disk is a flattened, rotating structure of gas and dust spiraling inward toward the black hole. As material in this disk moves closer to the black hole, it accelerates and heats up due to friction and gravitational compression. The inner regions of the disk can reach temperatures of millions of degrees, causing the material to emit intense radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. Not all of this material falls into the black hole, however. Through processes that astronomers are still working to fully understand, some of the energy and matter is redirected and accelerated outward along the black hole's axis of rotation, forming two oppositely directed jets that can extend far beyond the boundaries of the host galaxy. The exact mechanism that launches these jets remains one of the great unsolved problems in astrophysics, though several theories have been proposed. One leading explanation, known as the Blanford-Zenagic process, suggests that the jets are powered by the rotational energy of the black hole itself, extracted through interactions with the surrounding magnetic field. As the black hole spins, it drags spacetime around with it, a phenomenon called frame dragging. And this rotating spacetime, combined with magnetic fields threading the accretion disk, creates conditions that can accelerate particles to nearly the speed of light along the black hole's axis of rotation. Another theory, the Blanford-Payne mechanism, focuses on the accretion disk rather than the black hole itself. In this model, magnetic field lines anchored in the rotating disk act like cosmic slingshots, flinging material outward along the rotation axis. This process can occur even around non-rotating black holes, though the jets produced may be less powerful than those associated with rapidly spinning black holes. Webb's observations have revealed galactic jets of truly staggering proportions. One particularly remarkable example, observed by Webb in 2024, extends more than 23 million light-years from its source galaxy. To put this in perspective, our Milky Way galaxy is approximately 100,000 light-years in diameter, meaning this jet stretches a distance equivalent to 230 Milky Way galaxies placed end to end. This extraordinary jet, designated JWST GJ-1 James Webb Space Telescope, Galactic Jet 1, emanates from a galaxy located approximately 3.5 billion light-years from Earth. The jet itself appears as a thin, luminous filament extending in a nearly straight line from the galaxy's center, punctuated by several bright knots, where the jet material interacts with the intergalactic medium. The total energy contained in this jet is almost incomprehensible, equivalent to the energy that would be released by converting the mass of millions of suns entirely to energy according to Einstein's famous equation, E equals mc2. What makes this particular jet even more puzzling is that it originates from a galaxy that doesn't appear to have a particularly active nucleus at present. This suggests that the jet may be a relic of past activity, persisting long after the central black hole has entered a more quiescent phase. If so, this raises questions about how such structures can remain coherent over the immense timescales required for them to extend so far into intergalactic space. The concept of fossil or relic jets is relatively new in astronomy. Traditional models suggested that jets would dissipate relatively quickly once their energy source, the active galactic nucleus, shut down. However, observations like those from Webb are challenging this view, suggesting that jets can persist for much longer than previously thought, perhaps for hundreds of millions of years after the AGN becomes dormant. This persistence raises fascinating questions about the physics of these jets and the medium through which they travel. How do they maintain their coherence over such vast distances and timescales? What keeps them from dissipating into the surrounding intergalactic medium? The answers may lie in the magnetic fields that thread through the jets, potentially providing a structural framework that helps maintain their integrity long after the initial driving force has diminished. The composition and structure of galactic jets have also been revealed in unprecedented detail by Webb's infrared observations. The jets consist primarily of plasma, electrically charged particles, mainly electrons and protons, accelerated to speeds approaching that of light. These particles spiral around magnetic field lines that help collimate the jet, keeping it focused over vast distances. This collimation is one of the most remarkable aspects of galactic jets. Despite traveling for millions of light years, many jets maintain a relatively narrow, focused beam rather than spreading out in all directions, as might be expected. This focusing effect is primarily attributed to magnetic fields, which act like cosmic guide rails, constraining the charged particles to move along field lines rather than dispersing. Webb's infrared capabilities have allowed astronomers to study the detailed structure of these magnetic fields by observing the polarization of light emitted by the jets. When charged particles spiral around magnetic field lines, they emit radiation that is polarized in a specific way, providing information about the orientation and strength of the magnetic field. These observations reveal complex, helical magnetic field structures within the jets, supporting theories that magnetic fields play a crucial role in both launching and collimating these cosmic beams. As these charged particles travel through space, they emit radiation across the electromagnetic spectrum, from radio waves to gamma rays. Webb's infrared capabilities have been particularly valuable for studying the interaction between these jets and the surrounding intergalactic medium, revealing complex structures and shock waves that were previously invisible. When a jet plows into the tenuous gas of the intergalactic medium, it creates shock waves similar to those produced by a supersonic aircraft moving through Earth's atmosphere. These shock waves compress and heat the gas, causing it to emit radiation that Webb can detect in infrared wavelengths. The patterns of these shock waves provide information about the jet's speed, composition, and the density of the medium through which it travels. One of the most profound mysteries surrounding galactic jets is their energy source. The amount of energy required to power jets extending millions of light years is almost incomprehensibly large, equivalent to the energy that would be released by converting the mass of millions or even billions of suns entirely to energy according to Einstein's famous equation, E equals mc2. The leading theory suggests that this energy comes from the gravitational potential energy of material falling toward the black hole, combined with the rotational energy of the black hole itself. Through a process known as the Blandford-Zenagic mechanism, a spinning black hole can transfer some of its rotational energy to the surrounding magnetic field, which then accelerates particles outward along the black hole's axis of rotation. This process can be remarkably efficient, converting up to 40% of the infalling matter's rest mass energy into the kinetic energy of the jet, far more efficient than nuclear fusion, which converts less than 1% of mass to energy. However, the efficiency required for this process to generate the observed jets is at the very limit of what theoretical models predict is possible, suggesting that there may be additional mechanisms at work that we don't yet fully understand. One possibility is that the jets tap into the enormous rotational energy of the black hole itself. A spinning black hole contains a vast reservoir of rotational energy. A maximally spinning black hole with the mass of 1 billion suns would have rotational energy equivalent to the energy released by billions of supernova explosions. If a significant fraction of this energy could be extracted and channeled into jets, it could explain the extraordinary power observed in some galactic jets. Webb's observations have also revealed unexpected features within these jets, including knots, bends, and asymmetries that challenge simple models of jet formation and propagation. These features may result from instabilities within the jet, interactions with the surrounding medium, or variations in the output of the central engine over time. The knots observed in many jets are particularly interesting. These bright spots, spaced at irregular intervals along the jet's length, represent regions where the jet material is compressed and heated, causing it to emit more intensely. Some knots may form when faster-moving material in the jet catches up to slower material, creating a compression region similar to a traffic jam on a highway. Others may result from interactions between the jet and denser regions in the surrounding medium, or from variations in the jet's power as the central black hole's feeding rate fluctuates. Particularly puzzling are observations of jets that appear to bend or change direction over their length. Since the particles in these jets are traveling at speeds close to that of light, any significant change in direction requires enormous forces. Some of these directional changes may be due to the motion of the host galaxy through space, with the jet continuing in a straight line while the galaxy moves away from its original position. Others may result from interactions with intergalactic gas clouds or the gravitational influence of nearby galaxies. Webb's infrared observations have revealed several examples of jets that appear to curve gracefully across millions of light years, tracing vast arcs through intergalactic space. In some cases, these curved jets form beautiful, symmetric patterns, with both jets bending in opposite directions to create structures resembling cosmic S-curves. These patterns may result from the precession of the black hole's spin axis, a slow wobbling motion similar to that of a spinning top, causing the direction of the jet to change over time while maintaining its overall symmetry. The impact of these jets on their surroundings is another area where Webb has provided valuable insights. As jets propagate through intergalactic space, they can heat and compress the tenuous gas that fills the space between galaxies, potentially influencing the formation and evolution of other galaxies in their vicinity. This process, known as AGN feedback, is thought to play a crucial role in regulating galaxy growth throughout the universe. When a powerful jet encounters intergalactic gas, it can heat this gas to temperatures of millions of degrees, preventing it from cooling and condensing to form new galaxies. This negative feedback may help explain why we don't see as many large galaxies as cosmological models would predict. The jets from active galactic nuclei effectively limit galaxy growth by heating the raw material from which new galaxies would form. In some cases, jets may actually trigger star formation when they compress nearby gas clouds, while in others, they may prevent star formation by heating gas and preventing it from cooling and condensing into stars. This dual role as both creator and destroyer makes galactic jets important players in the cosmic ecosystem. Webb's observations have revealed several examples of positive feedback, where jets appear to trigger star formation in their host galaxies or in neighboring galaxies. When a jet impacts a dense gas cloud, it can compress this cloud, increasing its density and potentially triggering gravitational collapse that leads to the formation of new stars. These jet-induced star formation regions often appear as bright, blue knots of young stars aligned along the jet's path, providing visible evidence of the jet's influence on its surroundings. As you continue to relax and perhaps drift closer to sleep, consider the immense scales and energies involved in these cosmic fountains. The largest jets span distances that light itself takes millions of years to traverse, powered by processes occurring in regions smaller than our solar system, around black holes whose gravity is so intense that not even light can escape their grasp. These jets represent some of the most extreme physics in the universe, where the behavior of matter and energy is pushed to limits we can barely comprehend. Yet through instruments like Webb, we can observe and study these phenomena, gradually piecing together their mysteries and incorporating them into our understanding of the cosmos. The study of galactic jets connects some of the smallest scales in astrophysics, the event horizons of black holes, which can be smaller than our solar system, with some of the largest structures in the universe, jets extending millions of light years into intergalactic space. This connection across scales reminds us of the unity of physical laws, which govern phenomena from the quantum realm to the cosmic scale, and of the profound interconnectedness of the universe. As we prepare for our fifth cosmic lullaby, reflect on how these jets connect the smallest scales of black hole physics with the largest structures in the universe. A cosmic bridge spanning orders of magnitude in size and energy. Cosmic Lullaby 5, Rivers of Energy Flowing Through Space. As your body continues to relax and your mind drifts further toward the edges of sleep, imagine the vast rivers of energy flowing through the cosmic void. These galactic jets, streaming outward from the hearts of distant galaxies, trace luminous paths across millions of light years of otherwise empty space. Like rivers on Earth that bring life-giving water to their surroundings, these cosmic rivers transport energy and matter from the dense centers of galaxies to the sparse intergalactic medium. They connect the extreme environments near supermassive black holes with the vast, nearly empty regions between galaxies, creating a cosmic circulation system that distributes energy throughout the universe. The particles within these jets move at nearly the speed of light, approaching the fundamental cosmic speed limit. Yet from our distant perspective, they appear to flow with a serene, almost liquid grace, their movement imperceptible over human timescales despite their incredible velocity. As you continue to relax and perhaps drift closer to sleep, imagine following one of these particles on its journey. Accelerated near the event horizon of a supermassive black hole, it is channeled by intense magnetic fields into a narrow beam, joining countless others in a stream that will travel for millions of years across the intergalactic void. Along the way, it will pass near distant galaxies, through tenuous clouds of primordial hydrogen, perhaps even through the extended halos of hot gas that surround galaxy clusters. Eventually, it may encounter another galaxy or cloud of gas, transferring its energy in a collision that helps heat the intergalactic medium or perhaps triggers the formation of new stars. In this cosmic flow, we see a universe connected across its vastest scales, a universe where energy is neither created nor destroyed, but merely transformed and transported through the great cosmic rivers that are galactic jets. Imagine the journey of a single electron, accelerated to within a fraction of a percent of the speed of light, by the intense electromagnetic fields near a supermassive black hole. At these relativistic speeds, time dilation, a consequence of Einstein's theory of special relativity, becomes significant. From the electron's perspective, its journey across millions of light years might seem much shorter, while from our external viewpoint, this journey takes millions of years. As this electron travels along the jet, it spirals around magnetic field lines, emitting synchrotron radiation, a type of radiation produced when charged particles are accelerated in magnetic fields. This radiation spans the electromagnetic spectrum from radio waves to X-rays, contributing to the jet's luminous appearance. The electron's path is not perfectly straight, but follows a helical trajectory determined by the structure of the magnetic field threading the jet. The jet itself is not a solid object, but a flow of countless such particles, each following its own path while collectively forming a coherent structure maintained by magnetic fields. Like a river on Earth, the jet has regions of turbulence where particles move in complex, chaotic patterns, and regions of laminar flow, where they move more smoothly and uniformly. As the jet extends farther from its source galaxy, it gradually widens and becomes less dense, its particles spreading out as the confining magnetic field weakens. Eventually, the jet may terminate in a vast lobe where it finally dissipates its energy into the intergalactic medium, creating a diffuse cloud of energetic particles and magnetic fields that can persist for billions of years. Throughout this journey, The particles in the jet interact with the sparse matter of intergalactic space, primarily hydrogen atoms, with a density of perhaps 1 atom per cubic meter. These interactions gradually slow the jet and transfer its energy to the surrounding medium, heating it and sometimes causing it to glow faintly in wavelengths that Webb can detect. In this cosmic flow, we see a universe connected across its vastest scales, a universe where energy is neither created nor destroyed, but merely transformed and transported through the great cosmic rivers that are galactic jets. From the intense gravitational energy of matter falling toward a black hole, to the kinetic energy of particles traveling at nearly the speed of light, to the thermal energy of heated intergalactic gas. Energy flows through different forms, while maintaining the total cosmic balance described by the laws of thermodynamics. As you continue to relax and drift toward sleep, feel yourself becoming part of this cosmic flow, connected to the great rivers of energy that traverse the universe. Like the particles in these jets, we too are travelers through space and time. Our brief journeys part of the greater cosmic story that has been unfolding for billions of years, and will continue long after we have returned to stardust. Now, as we return to our exploration of the mysterious galaxies revealed by Webb, remember that there's no need to hold onto every detail. Simply allow the gentle flow of cosmic information to wash over you as you transition toward sleep, carried along by the rivers of energy flowing through space, UFO, galaxies, and hidden cosmic structures. As we continue our journey through the mysterious galaxies revealed by the James Webb Space Telescope, let's explore one of the most intriguing discoveries made possible by Webb's revolutionary infrared vision: the so-called UFO galaxies. These unusual cosmic objects remained completely invisible to previous telescopes, but have been revealed in surprising numbers by Webb's unique capabilities. As you continue to relax, allowing your breathing to become slower and your body to sink deeper into comfort, let's explore these hidden cosmic structures and what they tell us about the universe. The term UFO galaxies was coined by astronomers to describe a class of galaxies that were essentially undetectable before Webb. Unlike conventional galaxies that emit significant amounts of visible light, these galaxies are shrouded in such thick clouds of dust that virtually all of their visible light is absorbed. Only their infrared emission, which can penetrate these dust clouds, reveals their existence. To understand why these galaxies remained hidden for so long, it helps to understand the relationship between dust and light in the cosmos. Cosmic dust consists of tiny solid particles, typically less than a micrometer in size, composed primarily of carbon, silicon, oxygen, and other elements. These dust grains are extremely effective at absorbing and scattering visible light, particularly blue light, with shorter wavelengths. This is why dust clouds in our own Milky Way appear as dark patches against the background of stars. They are blocking the visible light from stars behind them. Infrared light, however, has longer wavelengths than visible light and can pass through dust much more easily. This is similar to how radio waves can pass through walls that block visible light. Webb's infrared detectors can therefore see through dust clouds that are completely opaque to visible light, revealing objects that were previously hidden. The first UFO galaxy was discovered in early 2023, just months after Webb began its scientific operations. Astronomers were examining what appeared to be an empty region of space when they noticed a faint infrared glow. Further analysis revealed that this glow came from a substantial galaxy that was completely invisible in all previous optical surveys of the same region. This galaxy, temporarily designated JWST UFO-1, appeared to be a massive spiral galaxy with active star formation. Yet it was so thoroughly enshrouded in dust that not a single photon of visible light from its billions of stars had been detected by previous telescopes. This initial discovery prompted a systematic search for similar objects, leading to the identification of hundreds and eventually thousands of these previously invisible galaxies. Webb's deep field observations, where the telescope stares at a seemingly empty patch of sky for extended periods to collect as much light as possible, have been particularly fruitful for finding UFO galaxies. In some of these deep fields, up to 10% of the galaxies detected by Webb had no counterparts in visible light surveys, suggesting they belong to this dust-enshrouded category. The existence of so many previously undetected galaxies has profound implications for our understanding of cosmic evolution. Galaxy surveys based on visible light have been used to construct models of how galaxies form and evolve throughout cosmic history. If a significant population of galaxies has been systematically missed in these surveys because they're hidden by dust, our models may need substantial revision. One of the most surprising aspects of UFO galaxies is their diversity. Rather than representing a single type of cosmic object, they span a wide range of sizes, shapes, and apparent ages. Some appear to be massive spiral galaxies similar to our Milky Way, but with much higher dust content. Others are irregular in shape, possibly the result of galactic mergers or interactions. Still others appear to be ancient elliptical galaxies, which typically contain older stellar populations and were thought to have relatively little dust. This diversity suggests that dust-enshrouded phases may be common in various types of galaxies at different stages of their evolution, rather than representing a distinct class of objects. A galaxy might go through periods where it is heavily dust-obscured, followed by phases where it is more visible in optical wavelengths. The dust itself is a crucial component of cosmic evolution. Dust grains provide surfaces where atoms can combine to form molecules, including complex organic molecules that may be precursors to life. Dust also plays a vital role in star formation, helping gas clouds cool and collapse to form new stars. Understanding the distribution and properties of dust in these heavily obscured galaxies can provide insights into these fundamental processes. Webb's spectroscopic instruments have allowed astronomers to study the composition of dust in UFO galaxies, revealing unexpected complexity. The dust contains not just simple compounds like silicates, similar to sand on Earth, but also complex organic molecules, including polycyclic aromatic hydrocarbons, PAHs, ring-shaped molecules that are among the most complex known to exist in space. These molecules absorb ultraviolet light from stars and re-emit it in specific infrared wavelengths, creating a spectral fingerprint that Webb can detect and analyze. The abundance of these complex molecules in UFO galaxies suggests that these cosmic environments may be important sites for the formation of organic compounds. While this doesn't directly indicate the presence of life, it does suggest that the chemical precursors for life may be more common in the universe than previously thought, forming even in these dust-enshrouded environments far from conditions we typically associate with habitability. Another intriguing aspect of UFO galaxies is their star formation activity. Despite being hidden from view in visible light, many of these galaxies show signs of intense star formation when observed in infrared wavelengths. This star formation is often concentrated in dense, dusty regions where visible light telescopes cannot penetrate. In some UFO galaxies, the rate of star formation is hundreds or even thousands of times greater than in our Milky Way, placing them in the category of starburst galaxies. These cosmic factories are producing new stars at a prodigious rate, yet their activity remained largely hidden until Webb's infrared eyes revealed it. This hidden star formation has implications for our understanding of the cosmic star formation history, the rate at which stars have formed throughout the universe's history. Previous estimates of this history, based primarily on visible light observations, may have systematically underestimated the star formation rate, particularly at certain cosmic epochs where dust-enshrouded galaxies were more common. The distribution of UFO galaxies through cosmic time is another area where Webb has provided surprising insights. Rather than being evenly distributed throughout cosmic history, these dust-enshrouded galaxies appear to be most common at specific cosmic epochs, particularly around 10 billion years ago, a period often referred to as cosmic noon, when star formation in the universe was at its peak. This concentration suggests that the conditions during this era were particularly favorable for the formation of dust-rich galaxies. Perhaps the higher overall density of the universe at this time led to more frequent galaxy interactions and mergers, which can stir up dust and trigger the intense star formation seen in many UFO galaxies. Alternatively, the chemical evolution of the universe may have reached a point where dust production was particularly efficient, with enough heavy elements available to form dust, but before processes that destroy dust became dominant. One particularly fascinating UFO galaxy, designated JWST UFO 42, appears to be undergoing a transformation from a dust-enshrouded state to a more visible one. This galaxy shows signs of powerful outflows of gas and dust from its central region, likely driven by the energy from a supermassive black hole that has recently become active. These outflows are in the process of clearing away the dust that has kept the galaxy hidden, potentially revealing it to visible light telescopes for the first time in perhaps billions of years. This galaxy provides a rare glimpse of a cosmic transition in progress, suggesting that the distinction between UFO galaxies and more conventional visible galaxies may be fluid, with individual galaxies moving between these categories throughout their long histories. The relationship between UFO galaxies and other unusual cosmic objects is another area of active investigation. Some UFO galaxies appear to be related to objects previously detected only in far-infrared and submillimeter wavelengths, known as submillimeter galaxies, SMGs. These objects were discovered by ground-based telescopes operating at wavelengths longer than those observed by Webb, and they were known to be dust-rich and highly star-forming. Webb's observations suggest that UFO galaxies and SMGs may be part of the same population, with Webb detecting the shorter wavelength infrared light and ground-based telescopes detecting the longer wavelength emission. However, Webb has also discovered UFO galaxies that were not previously detected even by submillimeter telescopes, suggesting they may represent an even more extreme category of dust-enshrouded objects. The connection between UFO galaxies and active galactic nuclei, and the bright, energetic regions at the centers of galaxies powered by supermassive black holes, is particularly intriguing. Many UFO galaxies show signs of AGN activity when observed in infrared wavelengths, suggesting that their central black holes are actively consuming surrounding material. This connection raises the possibility that the dust enshrouding these galaxies may be related to their AGN activity. The energy released by an AGN can heat surrounding dust, causing it to glow brightly in infrared wavelengths. Additionally, the processes that funnel material toward the central black hole, such as galaxy mergers or internal instabilities, can also stir up dust and trigger star formation, potentially explaining the dusty, star-forming nature of many UFO galaxies. Webb's observations have also revealed unexpected structures within UFO galaxies that were previously impossible to detect. Some show evidence of spiral arms, bars, or rings similar to those seen in visible galaxies, but composed primarily of dust and gas rather than stars. Others display more chaotic structures, with multiple clumps of star formation scattered throughout a diffuse cloud of dust. These structures provide clues to the formation and evolution of these galaxies. Ordered structures like spiral arms suggest that despite their dusty nature, these galaxies have had time to develop the gravitational stability associated with mature galaxies. More chaotic structures may indicate younger systems still in the process of settling into equilibrium, or galaxies that have recently experienced disruptive events like mergers or close encounters with other galaxies. The environments surrounding UFO galaxies have also yielded surprises. Many appear to be located in dense cosmic neighborhoods with numerous companion galaxies nearby. This suggests that interactions with these companions may play a role in creating or maintaining the dust-enshrouded state. Gravitational interactions with nearby galaxies can funnel gas toward a galaxy's center, triggering star formation and stirring up dust, potentially creating the conditions observed in UFO galaxies. In some cases, Webb has observed what appear to be streams or bridges of dust and gas connecting UFO galaxies to their neighbors, direct evidence of material being exchanged between these cosmic systems. These observations provide a glimpse of galaxy evolution in action, showing how galaxies grow and change through interactions with their environment. The future evolution of UFO galaxies is a subject of intense speculation among astronomers. Will they remain dust-enshrouded indefinitely? Or will processes such as AGN activity, intense star formation, or galaxy interactions eventually clear away the dust, revealing them to visible light telescopes? The example of JWST UFO 42, with its dust-clearing outflows, suggests that at least some UFO galaxies may eventually transition to more conventional visible galaxies. Alternatively, some UFO galaxies may be in a steady state, with dust creation and destruction processes in balance, allowing them to maintain their dust-enshrouded nature over long cosmic timescales. Others may cycle between dusty and more visible phases as their star formation rates and AGN activity fluctuate over time. As you continue to relax and perhaps drift closer to sleep, consider how Webb's infrared vision has literally revealed a previously invisible aspect of our universe. These UFO galaxies, hidden from view until now, remind us that our understanding of the cosmos is always incomplete, limited by our technological capabilities and the wavelengths of light we can detect. The discovery of thousands of previously unknown galaxies, some quite massive and active, hidden behind veils of dust, challenges our cosmic census and reminds us of the importance of multi-wavelength astronomy. Only by observing the universe across the electromagnetic spectrum, from radio waves to gamma rays, can we hope to build a complete picture of the cosmos and its evolution. These hidden galaxies also remind us of the dynamic, ever-changing nature of the universe. Galaxies are not static objects, but evolving systems that can transform dramatically over cosmic time, perhaps cycling between visible and dust-enshrouded states as they interact with their environment and undergo internal changes. As we prepare for our sixth cosmic lullaby, reflect on how much of the universe remains hidden from our direct view, waiting to be revealed by new technologies and observational techniques. Just as Webb has unveiled these previously invisible galaxies, future instruments may reveal other currently hidden aspects of the cosmos, continuing humanity's journey of cosmic discovery. Cosmic Lullaby 6. Veils of cosmic dust. As your mind continues to drift and your body sinks deeper into relaxation, imagine the delicate veils of cosmic dust that shroud the UFO galaxies we've been discussing. These veils, composed of countless microscopic particles floating in the vast spaces between stars, absorb and scatter light, hiding the brilliant galaxies behind them from view in visible wavelengths. These dust particles, though individually tiny, collectively form structures of breathtaking beauty and complexity. In visible light, they appear as dark clouds against the backdrop of stars, like shadows cast across the cosmos. But in the infrared wavelengths that Webb observes, they glow with their own warm radiance, revealing their intricate patterns and structures. Each dust grain has its own story, formed perhaps in the outer atmosphere of a dying star, expelled into space in a stellar wind or supernova explosion, drifting through the interstellar medium for millions of years, before becoming part of a vast cloud that obscures an entire galaxy from view. These grains have journeyed across light years of space, perhaps passing through multiple star systems before reaching their current location. Despite their light-blocking properties, these dust grains are essential to the cosmic story. They provide surfaces where atoms can combine to form molecules, including water, ammonia, methane, and even complex organic compounds. They shield forming stars and planets from harsh radiation, allowing more delicate chemical processes to unfold. They absorb ultraviolet and visible light, re-emitting it as infrared radiation that helps cool dense gas clouds, allowing them to collapse and form new stars. As you continue to relax and perhaps drift closer to sleep, imagine these veils of dust as cosmic cradles, nurturing the formation of new stars and planetary systems within their protective embrace. Within the UFO galaxies, behind their dusty veils, countless new worlds may be taking shape, hidden from view but part of the grand cosmic cycle of creation and transformation. The dust itself is not uniform, but varies in composition and size throughout these cosmic veils. Some regions contain primarily silicate particles, similar to tiny grains of sand. Others are rich in carbon compounds, including graphite and more complex organic molecules. The size of these particles ranges from molecules consisting of just a few atoms to relatively large grains a micrometer or more in diameter. Still far too small to see with the naked eye, but giants compared to individual atoms. This diversity in composition creates the complex infrared signatures that Webb detects, with different types of dust emitting and absorbing at different wavelengths. By analyzing these signatures, astronomers can determine not just the presence of dust, but its composition, temperature, and even its history, reading the cosmic dust like a book that tells the story of these hidden galaxies. The patterns formed by this dust are equally diverse. In some regions, the dust forms filamentary structures, long, thin strands that may stretch for hundreds of light years. In others, it creates shell-like structures around energetic stars, pushed outward by stellar winds and radiation pressure. In still others, it forms turbulent, chaotic patterns, stirred by the complex interplay of gravity, magnetic fields, and the energy from nearby stars. Within the densest dust clouds, where the dust is thick enough to block even most infrared light, the most profound transformations occur. Here, shielded from external radiation, gas can cool to just a few degrees above absolute zero. At these temperatures, gravity can overcome the thermal motion of the gas, causing it to collapse and form new stars. Around these forming stars, disks of dust and gas coalesce, eventually forming planets, asteroids, comets, and all the other components of stellar systems. This process of star and planet formation, hidden within the dusty veils of UFO galaxies, represents the universe's creative capacity. Its ability to transform diffuse matter into concentrated, organized systems capable of generating energy, and in at least one case we know of, supporting life. The dust that hides these galaxies from our visible light telescopes is not merely an obstacle to observation, but an essential component of this creative process. As you continue to relax and drift toward sleep, feel yourself enveloped in these gentle cosmic veils, protected and nurtured like the forming stars within their dusty cocoons. Like those stars, you too are part of the cosmic cycle, your atoms forged in stellar furnaces, and perhaps once part of the very dust that now shrouds distant galaxies from view. Now, as we return to our exploration of the mysterious galaxies revealed by Webb, remember that there's no need to hold onto every detail. Simply allow the gentle flow of cosmic information to wash over you as you transition towards sleep, carried along by the veils of cosmic dust that both hide and nurture the universe's creative processes. The future of galactic discovery. As we reach the final segment of our journey through the mysterious galaxies revealed by the James Webb Space Telescope, let's turn our attention to the future of galactic discovery and the profound questions that remain unanswered. While Webb has already transformed our understanding of the cosmos, its mission continues, with many more discoveries waiting to be made in the coming years. As you continue to relax, allowing your body to become completely at ease and your mind to drift peacefully, let's explore the cosmic frontiers that still await us and the philosophical implications of what we've learned about mysterious galaxies. Webb's observing schedule extends for many years into the future, with astronomers around the world competing for valuable telescope time to study a wide range of cosmic phenomena. Many of these planned observations will focus on distant galaxies, seeking to answer questions raised by Webb's initial discoveries. One major area of future investigation involves pushing the frontier of observation even further back in time, toward the very first galaxies that formed after the Big Bang. Astronomers hope to identify and characterize galaxies from the era of cosmic dawn, when the first stars and galaxies illuminated the previously dark universe. These observations may help resolve questions about how quickly galaxies formed and evolved in the early universe, and how they contributed to the process of reionization that transformed the cosmos from opaque to transparent. The era of cosmic dawn represents one of the last major unexplored epochs in cosmic history. After the release of the cosmic microwave background radiation about 380,000 years after the Big Bang, the universe entered a period often called the Cosmic Dark Ages. During this time, the universe was filled with neutral hydrogen gas, but contained no sources of light. This period lasted until the first stars and galaxies began to form, perhaps 100 to 200 million years after the Big Bang. These first luminous objects began to reionize the neutral hydrogen that filled the universe, gradually creating the transparent cosmos we observe today. This process of reionization is thought to have been completed by about 1 billion years after the Big Bang, but many details remain uncertain. When exactly did it begin? How quickly did it proceed? What types of objects were the primary sources of the ionizing radiation? Webb's observations of the earliest galaxies may help answer these questions, filling in this crucial chapter in cosmic history. The very first galaxies are expected to differ significantly from those we observe in the nearby universe. They would have formed from pristine gas containing only the elements produced in the Big Bang, primarily hydrogen and helium, with trace amounts of lithium. Heavier elements, which astronomers collectively call metals, were created later through nuclear fusion in stars and dispersed when those stars died, particularly in supernova explosions. These first galaxies, therefore, should contain few or no metals, a property that would give them distinctive spectral signatures that Webb can detect. By identifying and studying these metal-poor galaxies, astronomers hope to understand the conditions under which the first galaxies formed and how they evolved over time. However, Webb's early observations have already challenged some aspects of this picture. As we discussed earlier, galaxies like GNZ11 show surprising amounts of metals despite existing very early in the universe's history. This suggests that star formation and metal enrichment may have proceeded more rapidly than previously thought, or that the first stars were more efficient at producing and dispersing heavy elements. Future Webb observations will target even earlier galaxies, pushing closer to the theoretical limit of when the first galaxies could have formed. By building up a statistical sample of these earliest galaxies, astronomers hope to determine whether objects like GNZ11 are rare exceptions or representative of a broader population of surprisingly mature early galaxies. Another focus of future observations will be detailed studies of the unusual galaxies we've discussed throughout this journey. By examining larger samples of dead early galaxies, ring galaxies, galaxies with massive jets, and UFO galaxies, astronomers hope to determine whether these are rare exceptions or representatives of significant cosmic populations. This statistical approach will help clarify the diversity of galactic evolution pathways and the processes that shape galaxies throughout cosmic history. For example, if dead early galaxies like the one we discussed are found to be common, it would suggest that the processes that shut down star formation can operate much more quickly and efficiently than current models predict. This might indicate that feedback from active galactic nuclei, the energy released by supermassive black holes consuming surrounding material, plays a more dominant role in galaxy evolution than previously thought. Similarly, if UFO galaxies turn out to be abundant throughout cosmic history, it would suggest that a significant fraction of the universe's star formation and black hole growth has been hidden from view in previous surveys based on visible light. This would require revisions to our understanding of the cosmic star formation history and the growth of supermassive black holes over time. Webb will also continue to work in concert with other observatories, each providing different perspectives on the same cosmic objects. Radio telescopes like the Atacama Large Millimeter/Submillimeter Array ALMA and the upcoming Square Kilometer Array SKA can detect cold gas and dust in galaxies, revealing the raw materials for star formation. X-ray observatories like Chandra and the future Advanced Telescope for High-Energy Astrophysics, Athena, can observe the high-energy processes associated with supermassive black holes and galactic jets. By combining these multi-wavelength observations with Webb's infrared view, astronomers can build a more complete picture of galactic structures and processes. This multi-wavelength approach is essential because different components of galaxies emit radiation at different wavelengths. Stars, particularly hot young stars, emit primarily in ultraviolet and visible light. Cooler stars emit more in the near-infrared. Dust absorbs ultraviolet and visible light, re-emitting it in the infrared. Cold molecular gas, the fuel for star formation, emits primarily in radio and submillimeter wavelengths. Active galactic nuclei emit across the spectrum, but are particularly bright in X-rays. By observing across these wavelengths, astronomers can piece together a comprehensive view of galaxies that would be impossible from any single perspective. For example, combining Webb's infrared observations of UFO galaxies with radio observations from ALMA can reveal both the distribution of dust from Webb and the reservoirs of cold molecular gas from ALMA in these objects. This combined view can help determine whether these galaxies have the raw materials for continued star formation and how long their dust-enshrouded phase might last. Similarly, combining Webb's observations of galaxies with powerful jets with X-ray observations from Chandra can reveal both the structure of the jets themselves, from Webb, and the high-energy processes occurring near the central black hole that powers them from Chandra. This multi-wavelength view can help clarify the connection between black hole activity and jet formation, addressing one of the major unsolved problems in astrophysics. Looking further ahead, the next generation of space telescopes and ground-based observatories will build on Webb's discoveries, pushing our observational capabilities even further. The Nancy Grace Roman Space Telescope, scheduled for launch in the coming years, will have a field of view 100 times larger than Webb's, allowing it to survey vast areas of the sky and discover rare and unusual galaxies that might otherwise be missed. Extremely large ground-based telescopes, with primary mirrors 30 meters or more in diameter, will provide unprecedented resolution for studying the detailed structure of distant galaxies. The Roman Space Telescope, named after NASA's first chief astronomer, represents a different but complementary approach to Webb. While Webb excels at studying individual objects in great detail, Roman is designed as a survey telescope, capable of imaging large areas of the sky relatively quickly. This wide-field capability will allow Roman to conduct a cosmic census, identifying rare objects like the most distant quasars, unusual galaxy mergers, or galaxies caught in the act of transformation from one type to another. Roman will observe primarily in the near-infrared, overlapping with some of Webb's wavelength coverage, but not extending as far into the mid-infrared. This means that Roman will be particularly well-suited for studying the distribution of galaxies throughout the universe, mapping the cosmic web of dark matter through its gravitational effects, and identifying interesting objects for Webb to study in more detail. The extremely large ground-based telescopes currently under construction, including the 30-meter telescope, TMT, the Giant Magellan Telescope, GMT, and the European Extremely Large Telescope, ELT, will complement space-based observatories with their enormous light-gathering power and high resolution. These telescopes will use adaptive optics, systems that correct for the blurring effects of Earth's atmosphere, to achieve resolution comparable to or better than that of space telescopes for certain types of observations. These ground-based giants will excel at spectroscopy, the detailed analysis of light broken down by wavelength, allowing them to determine the composition, motion, and physical conditions in distant galaxies with unprecedented precision. They will also be able to image the structure of galaxies in extraordinary detail, potentially resolving features as small as individual star clusters or giant molecular clouds in galaxies billions of light years away. As these new instruments come online, they will undoubtedly reveal new mysteries and challenges to our understanding, continuing the cycle of discovery, puzzlement, and eventual comprehension that characterizes the scientific process. Beyond the technical aspects of future observations, the discoveries we've discussed raise profound philosophical questions about our place in the cosmos. The immense diversity of galaxies revealed by Webb suggests that the universe is even more varied and complex than we previously imagined. Each galaxy represents a unique evolutionary history, shaped by a combination of universal physical laws and the particular circumstances of its formation and development. This cosmic diversity mirrors the biological diversity we observe on Earth, where common processes of evolution have produced an astounding variety of life forms adapted to different environments and ecological niches. In both cases, we see the interplay of universal principles and particular circumstances producing a rich tapestry of forms and structures. The ancient galaxies we've discussed also provide a humbling perspective on cosmic timescales. The light from these distant objects has been traveling for billions of years before reaching Webb's mirrors, carrying information about conditions in the early universe. During that time, our own solar system formed, life emerged and evolved on Earth, and human civilization developed the technology to detect and interpret this ancient light. Our entire human history represents the briefest moment in the cosmic timeline. Yet, we have managed to extend our understanding across billions of years of cosmic evolution. To put this in perspective, consider that the light from GNZ 11, one of the most distant galaxies we discussed, left that galaxy about 13.4 billion years ago. During its journey to Earth, the universe expanded significantly, so that GNZ 11 is now located about 32 billion light-years away in terms of current distance. The light we observe left this galaxy when the universe was less than 3% of its current age, long before our solar system or even our galaxy had formed. During the billions of years that this light traveled through space, generations of stars lived and died in our galaxy. Our sun formed about 4.6 billion years ago, roughly 9 billion years after the light from GNZ 11 began its journey toward us. Earth formed shortly thereafter, and life emerged on our planet perhaps 3.8 billion years ago. Human beings in our modern form have existed for only about 300,000 years, less than 0.01% of the time that the light from GNZ 11 has been traveling. Yet despite our brief existence and our location on a small planet orbiting an ordinary star in one of billions of galaxies, we have developed the capacity to detect and interpret this ancient light, to understand its message from the early universe, and to piece together the cosmic story that connects us to these distant objects. Perhaps most profoundly, the study of distant galaxies connects us to our cosmic origins. The elements that make up our bodies, the carbon, nitrogen, oxygen, and other elements heavier than hydrogen and helium, were forged in the hearts of stars and dispersed through galaxies by stellar winds and supernova explosions. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were created in cosmic processes that we can observe playing out in distant galaxies. As the astronomer Carl Sagan famously noted, we are star stuff contemplating the stars. This connection is not merely poetic but literal. The atoms in our bodies have histories that stretch back to the early universe. The hydrogen atoms were created in the Big Bang itself, nearly 14 billion years ago. The heavier elements were synthesized in stars that lived and died before our sun formed, enriching the interstellar medium from which our solar system eventually coalesced. In this sense, we are not merely observers of the cosmic drama, but participants in it. products of the same processes of stellar evolution and elemental synthesis that we study in distant galaxies. Our existence is intimately connected to the cosmic history we seek to understand. As you continue to relax and perhaps drift closer to sleep, consider how the mysterious galaxies revealed by Webb are not merely distant objects of scientific interest, but part of the cosmic story that includes our own existence. The processes that shape these galaxies, star formation, elemental synthesis, galactic mergers and interactions, are part of the chain of events that eventually led to our solar system, our planet, and ourselves. In this sense, the study of distant galaxies is also a study of our own origins, a scientific exploration of the ancient cosmic processes that made our existence possible. As we peer deeper into space and further back in time, we are also looking deeper into the conditions that preceded and enabled our own emergence in the cosmos. The galaxies we've explored in this journey, from the ancient GNZ11 at the edge of the observable universe, to the bizarre, dead galaxy in the early cosmos, from the perfect symmetry of ring galaxies to the immense jets that connect the smallest and largest scales in the universe, from the previously invisible UFO galaxies to the future discoveries that await us. All are chapters in the grand cosmic narrative that includes our own brief but remarkable existence. As we conclude our journey through the mysterious galaxies revealed by the James Webb Space Telescope, remember that the exploration continues. Each new observation brings fresh insights and raises new questions in the endless cycle of discovery that characterizes our quest to understand the universe and our place within it. Now, as your body rests completely and your mind drifts peacefully, let's transition to our final thoughts, summarizing what we've learned about these cosmic mysteries and the questions that remain for future exploration. Final cosmic lullaby, our connection to the cosmic whole. As you drift toward the edges of sleep, feel your connection to the vast cosmic whole we've been exploring. Your body contains atoms that were forged in the hearts of ancient stars, atoms that have existed for billions of years, and have been part of the cosmic journey since long before our Earth formed. The hydrogen in the water molecules of your body was created in the Big Bang itself, nearly 14 billion years ago. The carbon that forms the backbone of your DNA was synthesized in the core of a star through the fusion of helium nuclei. The oxygen you breathe was likely produced in a massive star that ended its life in a supernova explosion, scattering its enriched material across interstellar space. These elements journeyed through the cosmos for billions of years before becoming part of our solar system, our planet, and eventually you. In this sense, you are not separate from the cosmos, but an integral part of it, a temporary arrangement of star-forged atoms that has developed the consciousness to contemplate its own origins. As you continue to relax and drift closer to sleep, imagine your consciousness expanding beyond the boundaries of your body, beyond our planet, beyond our solar system, to encompass the galaxies we've explored together. Feel your connection to the ancient light that has traveled across billions of light years to reach us, to the processes of stellar birth and death that created the elements of your body, to the cosmic cycles of creation and transformation that continue throughout the universe. In this expanded awareness, there is no separation between observer and observed, between you and the cosmos. There is only the flowing current of existence, the continuous transformation of energy and matter according to the fundamental laws of physics, a process that has been unfolding since the beginning of time and will continue long after our brief moment of awareness has passed. As you sink deeper toward sleep, allow this sense of cosmic connection to bring a profound peace. Your individual concerns and worries diminish in the context of cosmic scales and time scales. What remains is a sense of belonging to something vast and beautiful, a universe of infinite complexity and wonder that has produced, through its natural processes, beings capable of understanding and appreciating its grandeur. The mysterious galaxies revealed by Webb are not alien or separate from us, but part of the same cosmic family, shaped by the same physical laws, composed of the same fundamental particles, participating in the same grand dance of energy and matter that includes our own existence. In studying them, we are studying aspects of ourselves, our cosmic heritage, our elemental origins, our place in the vast tapestry of existence. As sleep approaches, let go of the need to remember specific details about the galaxies we've explored. What matters is not the retention of facts, but the expansion of perspective, the deepening of your connection to the cosmic whole. Let the rhythm of your breathing align with the cosmic cycles we've discussed, the birth and death of stars, the formation and evolution of galaxies, the expansion of the universe itself. In this alignment, you may find a profound rest, a peace that comes from recognizing your place in the cosmic order, neither insignificant nor central, but integral to the universe's ongoing story. Like a galaxy among galaxies, you are both unique in your specific arrangement and fundamentally connected to everything else through the shared history of your atoms and the universal laws that govern their behavior. Now, as you drift into the darkness of sleep, imagine it not as an absence, but as the cosmic void itself, the vast, mysterious space between galaxies filled with potential, governed by the same laws that shape the visible cosmos. In this void, as in deep sleep, the boundaries of individual existence soften, and we return temporarily to a state of unity with the cosmic whole. Good night, cosmic traveler. May your dreams be filled with the wonder of the universe, and may you awaken refreshed, carrying within you the expanded perspective that comes from contemplating the mysterious galaxies revealed by the James Webb Space Telescope, and your own profound connection to the cosmic story they tell. Conclusion. As we reach the end of our journey through the mysterious galaxies revealed by the James Webb Space Telescope, let's briefly recall the cosmic wonders we've explored together. We began by understanding Webb's revolutionary capabilities, its infrared vision allowing us to peer through cosmic dust and observe the most distant reaches of the observable universe. We explored how this remarkable instrument represents a quantum leap in our ability to observe the cosmos. With its 21-foot gold-coated beryllium mirror collecting infrared light that has traveled across billions of light-years of space. We then traveled to the edge of the observable universe to visit GNZ11, one of the most distant galaxies ever observed, existing just 400 million years after the Big Bang, yet showing unexpected complexity and composition. We marveled at how this ancient galaxy challenges our understanding of how quickly galaxies can form and evolve. With its surprising metal content, suggesting multiple generations of stars had already lived and died when the universe was less than 3% of its current age. We puzzled over the bizarre dead galaxy in the early universe, a cosmic object that seems to have formed and ceased star formation far more quickly than conventional theories would predict. We contemplated the mechanisms that could shut down star formation so early in cosmic history, from powerful active galactic nuclei to intense starbursts that rapidly consumed available gas. We marveled at the perfect symmetry of ring galaxies, formed through cosmic collisions, yet displaying beautiful, organized structures. We explored how these rings represent both destruction and creation, the disruption of one galactic structure leading to the beautiful, organized pattern of a ring, and the birth of countless new stars within it. We traced the immense galactic jets that extend millions of light years from their source galaxies, cosmic rivers of energy and particles that connect the smallest scales of black hole physics with the largest structures in the universe. We contemplated the enormous energies involved in these jets and the mechanisms that could launch and collimate them across such vast distances. And we discovered the previously invisible UFO galaxies, objects that remained hidden from view until Webb's infrared eyes revealed their existence. We explored how these dust-enshrouded galaxies challenge our cosmic senses and remind us of the importance of multi-wavelength astronomy for building a complete picture of the universe. Throughout this journey, we've encountered mysteries and surprises, observations that challenge existing theories and force astronomers to reconsider their understanding of galactic formation and evolution. These mysteries remind us that despite centuries of astronomical observation and decades of space-based astronomy, the universe still has many secrets to reveal. As you drift toward sleep, carry with you the wonder of these cosmic discoveries. The universe is more vast, more varied, and more mysterious than we ever imagined. Yet through instruments like Webb, we can explore its farthest reaches and oldest epochs, connecting our brief human moment to the grand cosmic story that has been unfolding for billions of years. Remember that you are part of this cosmic story, your atoms forged in ancient stars, your existence made possible by the same physical laws that shape the distant galaxies we've discussed. As you sleep, the universe continues its slow dance of creation and transformation, and Webb continues its silent watch, gathering the ancient light of distant galaxies to further our understanding of the cosmos we call home. Good night and pleasant dreams of cosmic wonders.